In this video, we're going to introduce some conceptual aspects of special and general relativity. Okay, so Einstein's special relativity, special and general relativity. We're going to see the conceptual part and the detailed theoretical working out of all the results. You can check out any textbook on it. Okay, so relativity existed even before Einstein, right? So if you have, let's say, you have an observer, or if you have somebody moving in a car moving at 50 kilometers per hour, and if another car is moving at 30 kilometers per hour, we all know that A is going to observe B, the relative motion, due to the relative motion, A is going to observe B only at 20 kilometers per hour. This was always known. Okay, but this is what Einstein does. Okay, so this is where Einstein's contribution to relativity comes. So Einstein says Maxwell's equation says that the speed of light is a constant. It says that electromagnetic radiation, which is nothing but light, is the speed of light a is nothing but c is equal to 1 by square root of mu naught epsilon naught, which are fundamental constants. They don't depend on the distances. How do you compute velocity? You compute velocity based on the distances and the time you observe, right? The clocks you need, what do you need? You need rulers and clocks to measure time, velocity, right? But the speed of light is not computed like that. It is found out from fundamental constants which don't change from relative observers, right? So therefore, Einstein is saying if supposing B was a flash of light from a torchlight, let's say B is a flash of light from a torchlight, and it is moving at, for the purposes of this lecture, we will say it is moving at 100 kilometers per hour. So this is a flash of light. So the speed of light is not 100 kilometers per hour. We all don't know that. It's 3 to 10 power 8 meter per second, but for purposes of this lecture. So this is a flash of light. So somebody is flashing a torchlight and it is moving at 100 kilometers per hour. So therefore, according to normal relativity, or what is called as Galilean relativity, you should observe this as 50 kilometers per hour, right? But the speed of light is not computed as other things like distances and times. It is a constant, right? It is a fundamental constant. So whoever observes it from any reference frame uh, is going to observe that the speed of light, okay, let's say it is 100 kilometers per hour, it's a constant, then he's going to observe only 100 kilometers per hour. The relative speed is going to still observe as 100 kilometers per hour, even though this person is traveling at 50 kilometers per hour. So somebody is flashing a speed of somebody is flashing light which is speed is 100 kilometers per hour, but this person is moving at 50, so he should observe it at 50, the relative due to the relative velocity, but he still observes it as 100 because the speed of light is a constant determined by fundamental constant. Therefore, if velocity is not changing, right? If velocity is not changing, then velocity is computed as distance over time. Then distance, your rulers and clocks, right? How you measure velocity, rulers and clocks, that is changing, right? Because it appears as though velocity here is the speed of light is the same, right? Then it should be that the speed of light is actually speeding up for this person because he's moving at 50. You should observe it at only 50 because the relative motion, but he's still observing it as 100, right? Therefore, it should be that speed of light is either speeding up, or it could be that the rulers and clocks that you are using, they are changing, right? There is a scaling of the rulers and clocks that you are using. So that is the fundamental argument. Okay, that is the fundamental argument. So by how much are they changing? But what are the uh, scaling factors involved? So this is the scaling factors involved in scaling your rulers and clocks. So time is scaled by a factor of gamma, which is 1 by 1 minus u square by c square. Okay, so this is your Galilean relativity, except if you take off this scaling factor, okay, of gamma, this is simply your Galilean relativity. Now time is scaled by this factor of gamma and beta. So this beta is nothing but u by c square. Okay, it's nothing but u by c square. Beta is nothing but u by c square. So this is the rescaling that is happening. So you can follow the argument again. So as I'm saying, flash, you have somebody traveling at 50 kilometers per hour. Okay, speed of light is 100 kilometers per hour. Somebody is flashing a torchlight. It's going at 100 kilometers per hour. So what should be the speed that this person observes? He should observe 50 kilometers per hour. But it cannot be so, because the speed of light is constant for all frames of reference. So it should be 100 kilometers per hour that he observes, right? So what can happen is that he it appears as though the light is speeding up first, because he should observe only at 50, but he's under observing 100, right? But the speed of light still is the same, right? So velocity is nothing but x by t, right? So if the speed of light is appearing as though it's speeding up, then what can change? Your distance, that the rulers and clocks that you are using to measure your velocity, right? Because velocity is x by t. The rulers and clocks that you're using is being changed, or is it's getting changed. Okay, it's getting changed. That is why this speeding up is happening. Okay, because it's actually not speeding up, right? It's the same. So if it is the same, then your rulers and clocks that you're using is changed. Okay, it's changing. So that's why we have this rescaling of the position and your time coordinates, right, by this amount. Okay, this gamma and beta factor, right? So what this introduces is, it introduces something called, these are the results of special relativity. So it introduces something called length contraction, time dilation, and mass dilation. So length, we knew that it was in in our normal world, we know that due to relative motion, length is not going to change. But in special relativity, due to this constancy of speed of light between the observers, what is going to happen is, there is a, because of this rescaling of this transformation coordinates, right? Because of the rescaling that we introduced, this gamma and beta, the length is going to get contracted. So if somebody moving close to the speed of light, let's say x prime, okay, the relative speed between them is u, it is close to the speed of light, then if a and b, let's say they're observing a rod, okay, let's say they're observing a rod, then what is going to happen is, the length is going to get contracted. The length is going to get contracted for the observer x. Okay, length is going to get contracted by this amount, the amount by which the, how it is closer to the speed of light. So if it is closer to the speed of light, length is going to get contracted. If it is equals the speed of light, the relative motion velocity, then it is going to become shrunk to a point. Okay, it's going to become a point. The rod is going to become a point. So similarly, time can dilate. So time dilation. So as you go closer to the speed of light, the time is going to slow down. When you hit speed of light, time is going to stop. Okay, if you travel faster than the speed of light, time is going to reverse. But, or negative time. So negative time is taken to be, in a physical sense, time reversal. But that cannot happen for a massive particle, because as your mass, as you travel faster and go closer to the speed of light, what is going to happen is, your mass is going to increase. This m naught is called your rest mass. Okay, and let's call this mr, or the relativistic mass, because here they are given v, the notation v is the mass observed due to the relative motion v. We'll call this the relativistic mass. So the relativistic mass is going to increase, and as when you hit the speed of light, the mass is going to become infinity. Okay, mass is going to become infinity. Now because of that, you will need an infinite amount of energy to accelerate any massive particle beyond the speed of light, which just means that you are not going to be able to accelerate the particle beyond the speed of light. So for any massive particle, the speed of light is said to be the limit. Okay, only virtual particles which don't have mass can travel faster than the speed of light. Now, one of the principal results of Einstein's special relativity is the equation that you would have come across in many places. E is equal to mc square. Okay, it comes because we put this relativistic mass in the kinetic energy formula, mr b square. When we put this relativistic mass, when you substitute this equation, you actually get this formula. What this says is, so this is your rest mass, E is equal to mc square. So what this says is that the energy and mass are the same quantities, but for a factor c square, constant factor c square. So energy and mass are proportional. Energy and mass are proportional. Okay, energy and mass are proportional. So what do we see here happening is that this relative motion, okay, relative motion between two frames, which you can think of as the kinetic energy, right? The kinetic energy is introducing some rescaling of the coordinates. Okay, your coordinates are getting squished and stretched, right? So supposing, let's say, this will take these as our coordinates. So this is our coordinates. This is x, x and t. So due to relative motion, what is happening? The coordinates are getting squished, okay, and so your lengths are getting contracted, right, and your time is getting dilated, right? The time intervals are getting dilated. This is what is happening, right? So this is so x and t, right? So relative motion. So this is what is happening, right? So we can see that due to the relative motion, the coordinates are now getting squished and stretched, right? Length contraction and time dilation. Your intervals are getting squished and stretched. So your energy, in a sense, is affecting your space and time. It's squishing and stretching your space and time. And once Einstein has already established this, mass and energy are equivalent by this factor, right? Mass and energy are equivalent by this factor c square, or they are proportional. So therefore, what he can say next is, he can say that mass is going to distort space-time. So this is the formula. This is nothing but general relativity. He goes on to say that mass can distort space-time. Okay, so these are pictures that you would have seen in some movies or things like that, or some pictures of general relativity. So we're going to see what this formalism is about. Okay, so what is this general relativity? So look, already the conceptual idea I've given it to you. Okay, so what happens is, in special relativity, what is the invariant quantity? In in our normal world, we know that length is an invariant quantity, right? So ds square, the interval ds square, dx square plus dy square plus dc square. So this is Pythagoras theorem in 3 dimensions. Right? This quantity is a invariant quantity, right? This is Cartesian coordinates, right? This is Cartesian coordinates. This quantity is invariant, and we normally say this, the coefficients of these terms are the scale factors. It's called the metric. So this is the metric in Cartesian coordinates. We have no cross terms here. This is the metric, right? So in a mathematical physics, you will see the study of coordinates. So if you see that, you will know what we're talking about here: Cartesian, spherical, and cylindrical. And what happens in special relativity? You will know that this no longer the position and time are independent variables. So far you would have studied as position and time as independent variables. X and t are independent. So no longer that will be the case, because what is happening here? These equations are mixing up position and time together as functions of each other. No longer they are independent, right? So no longer by these equations, position and time are getting mixed up and they're no longer independent, and therefore we cannot consider them independent, and that's why we no longer have length as a invariant quantity. Length is getting contracted between two frames due to the relative motion. So this quantity is no longer going to be invariant, and this is the quantity that is going to be a invariant. Okay, so in special relativity, the metric is going to be, so this is your metric, right? Metric of Cartesian space. This is your metric in special relativity. So metric, so we have the coefficients which we collect here. So this is going to be 1, 1. So we have 4-dimensional space-time. So far we have seen only 3-dimensional. So 4-dimensional space-time. This is your invariant quantity. So I've collected the coefficient here: 1, 1, 1, minus 1, and no cross terms: 0, 0, 0, 0, 0. So you might remember that we had for spherical, right? For spherical coordinates, we would have done, for spherical coordinates, you would remember the metric, right? So the metric was spherical coordinates, one r sine theta, right? This was your metric for spherical coordinates, right? So this was the invariant factor. So if you write out the invariant factor for the metric, we have dr square r square d theta square plus r square sine square d phi square. Okay, this was a metric in the spherical coordinate system, right? So spherical coordinates, you may, so a sphere, it has a positive curvature, right? So the sphere has a curvature, but a Cartesian coordinate, this does not have any curvature, right? So a Cartesian coordinate, we say that it does not have curvature, it's a flat space, right? But this sphere, the sphere here, the spherical coordinates that we can use to study systems that have some curvature. A space that has some curvature, we can use spherical coordinates to study, right? A space that is has a spherical space has some curvature. But the metric in special relativity, this is the metric. This is the metric. Now, why are we talking about this? Why are we talking about this? We are talking about this because we've said already, due to mass energy equivalence, Einstein is saying already that mass is going to distort space-time, because energy, we have already seen how kinetic energy, the relative motion, right? When motion is associated to kinetic energy, it's squishing and stretching space-time. Okay, it's distorting space-time. So by mass energy equivalence, mass is also going to distort space-time, right? So that's what visually depicted here. Mass is distorting space-time, and when mass distorts space-time, what we are interested to find is our metric of that space. Okay, we are going to find the, we are interested to find the metric of that space, because by the metric of the space, we can know what kind of space that is. Okay, we can know what kind of space that is, and we will be able to know what kind of space or what kind of coordinates we have to impose to study that space. By knowing what kind of coordinates we can impose to study that space, we can know what kind of space that is. So what is the, how are we going to depict this? By an equation. So this is established by the Einstein field equations. Okay, So this is the Einstein's equations in general relativity. So the right hand side, we said that the mass is going to cause the curvature. So that mass is going to be captured by your stress energy tensor. So the T mu nu is your stress energy tensor. Okay, so the stress energy tensor, so it is a two component tensor. That means in 4 dimensions it is going to have 16 components. Okay, so this, so the first component, so if you have only diagonal components and if you don't have cross terms, first component is an energy component. Next we have a momentum, the three momentum coordinate components in the three position coordinates. So if it is x, y, z, this is momentum in x coordinate, momentum in y coordinate, and momentum in z coordinate. And energy is going to be, energy is a scalar, right? Energy is a scalar. So energy is going to be the same, right? In all the components, right? In all the, and so energy is going to be, it's a scalar. So therefore, we are going to, uh, so this is a stress energy tensor. It's going to have 16 components, and if there are no cross terms, it will have only diagonal components. Now this position and momentum, okay, this position and momentum, sorry, this energy and momentum is unified. So we, just like I said, special relativity mixes up space and time, right? I said special relativity mixes up space and time, right? So therefore, we in special relativity we have four vectors, right, which unify this position and sorry, this momentum and energy. Okay, because I said in special relativity, no longer position and time are independent quantities; they are mixed up together, right? That's why we have this metric. Okay, that's why we have this metric. They get mixed up together, and because of that, we have something called four vectors in special relativity. And in the momentum four vector, energy and momentum get united, energy and momentum get, they get united into a single four vector. Okay, that is what the stress energy tensor is. And when it is in, and when we are talking about the, when we are talking about uh, when we don't have cross terms, it just becomes the four diagonal components. When we have cross terms, it will become 16 components. It will have 16 components. So this mass or this energy, because mass and energy are equivalent, is going to introduce space-time distortions, right? The cause is on the right hand side, the effect is on the left hand side. Okay, the effect is what is going to be the distortion of space-time, right? The distortion of space-time can be captured by your scalar, your curvature tensor, your curvature tensor, or your scalar and your scalar curvature. So r, mu, nu, and r. And what kind of space can be imposed to study this curvature can be known by the metric tensor, right? So here, if the space is distorted like a sphere, okay, because supposing you can introduce spherical coordinates to study that sphere, that space that is distorted, then we will have metric that has a, that looks like your spherical coordinates, right? So spherical coordinates, we have a curvature because sphere is curved. So depending, so the cause is here on the right hand side, the effect is here, and these are nothing but some constant. So this lambda, this is your cosmological constant. This quantity is your cosmological constant. This g is your gravitational constant. C is your speed of light. So this is the equivalence Einstein establishes, that due to space, the space-time distortions are nothing but are introduced because of mass. Okay, are introduced because of mass. So most, in all cases in special relativity, we will know this quantity. We have to find out the metric of the space. We have to find out the metric. We know the cause, right? If we know the cause, we have to find out the effect, which is the curvature introduced in that space due to that mass, and that can be known by the kind of coordinates that you can impose on the system to study, which will be revealed by the metric of the space, right? So these metrics reveal the kind of coordinates. We know the kind of coordinates you can impose on the space to study the space. That will tell us about the curvature of that space and all about that space. So this is what general relativity is about. Okay, so if you see a textbook, you will see the detailed working out of all these concepts. And if in a specific case, okay, you've seen that in movies they say that black holes, nothing can escape a black hole. So why is that, right? So we see that time dilation, we've already discussed time dilation, and this is due to distortion of space time, right? So if the mass of the black when the mass of the black hole, so the black hole is so heavy, so it's going to distort space time so much that the time is going to get dilated so much that there is no passage of time in the black hole. That time stands still. If time stands still, then no event can happen. If no event can happen, then nothing can escape the black hole, in the sense that no event can happen. So if you flash a speed, if you flash a light, it is not going to travel because the time has already stopped, right? If you're saying that something is going to travel, then it means that time is elapsing. But if time is stopped, then nothing happens, right? So that's why we say that these black holes, the nothing can escape the black hole because mass is so much that it distorts space time so much that the time dilation happens so much that no event can happen. So this is about special and general relativity. So hope you like these videos. So do read a textbook on this. Don't rely on this lectures. This is just to give you a conceptual framework to understand what is given in your textbook, the theory and all the details that are worked out. Okay. So thank you for watching. Do subscribe and let your friends know if you like this content. Thank you for watching.